Hello everyone and welcome back. In this video, we're going to talk in more detail about vector length. And we're also going to talk about a vector operation called scaling, which is an operation designed to change a vector's length. So first of all, some notation. If you have a vector written as v with the little vector arrow on top of it, the magnitude of v can be represented symbolically in a couple of different ways. One way to symbolically represent the magnitude of a vector v is to surround the vector v by a single set of vertical bars. I think this notation is a little bit dangerous, especially for students who are just getting started, because many students who are just getting started will see the vertical bars and get confused between this notation and the notation for absolute value. So I just want to emphasize that if you see this notation, the vertical bars are context dependent. If you see the vertical bars around a scalar like -3, that is talking about absolute value. Whereas if you see the vertical bars around a vector quantity like -3, 2 in brackets, that's talking about the magnitude slash the length of the vector -3, 2. So these vertical bars change their meaning depending on what is inside the bars. Now, what you'll often see me do in class to avoid this confusion is use an alternative way of denoting the magnitude of a vector, which is to surround the vector by two vertical bars, double vertical bars. It can become annoying if you have a problem with a lot of length calculations in it to carry the bars throughout the entire problem. But I do find that this notation is best in terms of making sure that students don't get confused with the absolute value. In physics, you'll see really my least favorite notation for magnitude, which is to write the letter V without the vector arrow. This is how the physicists will denote the magnitude of a vector quantity. They'll write the vector with the arrow, and they'll refer to the magnitude by just removing the arrow. Again, as a math teacher, in my opinion, this notation is very, very dangerous for students who are just getting started because it's very subtle, right? And it's very easy to get confused. I want you to be aware of this notation, but I personally will never use it. Now, if you're going to calculate the magnitude of a vector from its components, you can do that just using Pythagorean theorem slash the distance formula. So for example, if someone gave me the vector v, again being equal to -3, 2, and they wanted me to find the magnitude of the vector v, if I think about what the vector v looks like when it's drawn in two-dimensional space, this vector v will extend 3 units over here in the negative x direction, and it'll extend 2 units in the positive y direction. So if I want to figure out how long this vector is, the magnitude of this vector, I would just use Pythagorean theorem to find that length. And I would use Pythagorean theorem, the square root of the x component squared plus the y component squared. Basically, a squared plus b squared equals c squared in this picture. So after simplification, we would get a magnitude of square root 13 units for this vector. And the same overall formula and process applies for vectors that are three-dimensional. If I want to find the length of this vector, 1 comma -1 comma +2, then I'd find the magnitude of that vector by taking the square root of the x component squared, the y component squared, and the z component squared all added together, giving me an answer of square root 6. Just the 3D distance formula, just the 3D Pythagorean theorem can be used to find the magnitude of 3D vectors. Now, some terminology here, which for our class is going to be very, 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 very important. It's this piece of terminology that is actually the entire reason that I started giving language tests in the class. So a unit vector is a vector which has a length of exactly 1. A unit vector is a vector of length 1. And one way to remember where this name is coming from is that if you remember the unit circle from trig, the unit circle was this circle of radius 1 centered at the origin. And something to remember about unit vectors is that when you draw them, they will always point to a location on this unit circle. Because the unit circle points are 1 unit away from the origin, and a unit vector has a length of 1. So to make sure that we understand this language, I'm going to give us a lot of different vectors, and we're going to determine which of these vectors count as unit vectors. So for example, if I have the vector 0, -1, 0, is that a unit vector? To answer that question, all we have to do is calculate the vector's length, which would be the square root of 0 squared, -1 squared, and 0 squared. So that's square root of 1, and that's 1 indeed. So because this vector has a length of 1, it is verifiably a unit vector. You can also see that at the beginning of the problem without necessarily having to do any Pythagorean theorem. This vector has a 0x component, a 0z component, and a y component of -1. So this vector points 1 unit in the negative y direction. So it has a length of 1, so it is a unit vector. What about this vector 1, 1, 1? Is this a unit vector or not? Again, we can always check this by calculating the length directly. If I calculate the length directly using the distance formula, I end up with the square root of 3, which is not equal to 1. And therefore, this vector is not a unit vector. And again, we can actually tell at a glance that this vector is not the right length to count as a unit vector. Because this first component is already 1 unit long, the other two components here are just making the vector even longer than that. So this vector's length is greater than 1 for sure, which means it's not a unit vector, guaranteed. What about this vector? Is this a unit vector or not? Again, the most reliable way to check is to go ahead and calculate the length of this vector using the length formula. 1 over 2 squared, 1 over 2 squared, and 0 squared. If I simplify that, then I get 1/4 plus 1/4 under the root. Following PEMDAS, that would be combined to a 2/4 under the root, and so that would be equal to the square root of 1/2. So I can tell that that is not equal to 1. That's a little bit too small now, actually. This is too small. So as a result, this guy is not a unit vector. It's too short to be a unit vector. Now, what if we replace that 2 in the denominator with a square root of 2? In this case, when we go to calculate the length of the vector using the length formula, the square root in the denominator and the square in the formula cancel out. So we end up under the root with 1/2 plus 1/2 plus 0. So we end up with a 1 under the root, and so the square root of 1 gives us a length of 1. Therefore, yes, this guy is a unit vector. And for the final example, someone gives me the vector 3, 1, 6. I think we can answer this question without doing any calculations at all, right? There is no way this guy is a unit vector. It is obviously way too big. Already, just the x component is too big, right? Just the x component of 3 already makes the vector too long. Not to mention all the other components, 1 and 6, which are also contributing to the length. A unit vector is a vector whose length is 1, precisely 1 unit. So now let's talk about an operation which is called vector scaling. And when we talk about scaling, that word means multiplying a vector by a scalar. So something, for example, like taking the vector 2 comma minus 5 comma 1 and multiplying that vector by a scalar like 3. Vector scaling is multiplying a vector by a scalar. Now, vector scaling, just like addition and subtraction, is done component-wise, which means that if you want to multiply a vector by 3, for example, then you just have to multiply the x component by 3, the y component by 3, and the z component by 3. So for example, if they gave me the vector v equals 2, comma, minus 1, comma, minus 5, and they asked me to scale that vector by a factor of 3 and calculate 3 times this vector, all I would have to do is multiply each individual component by this 3. So 3 times 2, 3 times -1, 3 times -5, giving me an answer of 6, -3, -15, component-wise scaling. Once again, vector scaling is something that is used pretty often in even the most basic physics calculations involving force. For example, suppose that we have a 5-kilogram object moving in two-dimensional space. And this time, what we know about the object is its acceleration vector. It's accelerating along the vector 2, comma, -1. So if this is the acceleration that the object is experiencing, if it's being pulled in the positive x direction and in the negative y direction, let's figure out what is the net force acting on this object. Now, what's going to save us, again, is another foundational physics equation, which relates net force, acceleration, and mass. And the equation that we're going to use is the equation F equals ma. The net force vector is equal to the mass scalar times the acceleration vector. Net force vector, acceleration vector, and the mass, which is a scalar. Because in this equation, we're multiplying the acceleration vector by the mass scalar, this is an example of vector scaling. So let's use the data given to us in this problem and plug that into this equation. The net force is equal to the mass, here 5 kilograms, scaling the acceleration vector 2 comma minus 1. So if I then follow through on this component-wise scaling, I'd have 5 times 2 equals 10, and 5 times negative 1 equals minus 5. So this would be the net force experienced by this object that's causing it to accelerate in the positive x direction and the negative y direction. It's accelerating this way because the forces are pulling it this way. Now let's talk about how vector scaling changes the length of a vector. For example, suppose that my original vector is 3, 4. The length of this original vector is, by Pythagorean theorem, 3 squared plus 4 squared. So you might recognize that as a pretty famous 3, 4, 5 triangle situation. Length is 5. Now let's see what happens to the vector when it is scaled by a factor of 2. If I take the vector and multiply it by 2, I get the vector 2v, which is equal now to 6, 8. And if I find the length of 2v, then I will have the square root of 6 squared plus 8 squared. So this is the square root of 36 plus 64. This is the square root of 100, and that is 10. So something I want to observe is that when we scale the vector v by a copy of 2, the result was that the length also got scaled by a factor of 2. The same thing will happen if I scale the vector by a smaller factor. For example, let's scale this vector by a factor of 1/5. If I take the vector v and scale it by a factor of 1/5, that's going to give me 3 over 5 and 4 over 5. If I find the magnitude of this guy using the Pythagorean theorem, I have 3 over 5 squared plus 4 over 5 quantity squared. That's the square root of 9 over 25 plus 16 over 25. That is the square root of 25 divided by itself. That's the number 1, right? So this scaling, to use the language of the class, to practice that language, this scaling has turned v into a unit vector because it now has a length of 1. It's taken the length we used to have, 5, and it has basically eliminated that length. It's turned 5 into 1 by this factor of 1/5. So if one bears this in mind, that scaling a vector has the effect of scaling its length by the same amount, you can change a vector's length to whatever you desire. So for example, suppose that I have an object that's moving along direction 1, 1 with a speed of 25 meters per second. And I would like to write this object's velocity vector. First, I'm going to show you an incorrect approach to this problem. I'm going to show you an approach to this problem that is not correct, and then we'll show you what is the correct approach to this problem. My object is moving along this direction 1, 1. My velocity vector is also going to point in the same direction of movement, but it needs to be longer because the speed is equal to the magnitude of the velocity. So I want this velocity vector to be 25 units long. 25 units to match the speed at which the object is moving. So far that reasoning is valid, but here's the common mistake. The common mistake is to try and create the velocity vector by scaling 1, comma 1 by a factor of 25. I claim that this velocity vector is incorrect. I claim that this velocity vector is actually longer than it's supposed to be. Let's go ahead and check the length of this velocity vector that we've made. So using the standard Pythagorean theorem, I have 25 squared plus 25 squared under the root here. So that's 2 copies of 25 squared. And so if I simplify this root, I get 25 times square root 2. So as a decimal approximation, what we're finding is that our speed is actually significantly too big now, right? As a decimal, this is approximately equal to 35.4 meters per second, not the 25 meters per second that my velocity vector is supposed to have for its magnitude. So although this reasoning was correct, we want to create the velocity vector by extending the direction so that it has a length of 25. But this approach of just multiplying 1 comma 1 by 25 doesn't work. It gives us a velocity vector that's too long. So instead, let's go ahead and fix this approach. I do want to create the velocity vector by scaling the direction vector by some number. But it's not going to work if I just scale the direction vector by 25. Instead, let's take the magnitude of both sides of this equation and recognize that I need the velocity vector to have a magnitude of 25 in the end. So let's try and solve this equation for the correct value of c. Now let's recall from earlier that when you scale a vector by a constant, the effect is that the length of the vector is also scaled by that constant. So I'm going to use that fact here to say when I scale the direction vector d by this constant c, the result is that the length of that vector is also scaled by that same constant. So now if I want to know what value of c I should use as my scalar, solving this equation, I find that my value of c should be 25, the desired length, divided by the magnitude of the direction vector divided by my current length. So to rescale this vector so that it has a length of 25 in the end, I need to take the vector, divide out the length it has right now, and then multiply by the length of 25 that I want. So let's figure out the length of the direction vector that I have right now. The length of the direction vector 1 comma 1 is equal to the square root of 1 squared plus 1 squared. So that's square root 2. And that tells me that my velocity vector should be obtained by taking 1 comma 1, dividing it by the length it has right now, and then applying the length that I want, then applying the 25. So the velocity vector is going to be the vector 25 over root 2 and 25 over root 2. And this vector will point in the correct direction and have a length of 25 units in the end to match the given object's speed. Let's practice this concept several more times. Somebody says, find a unit vector that points in the same direction as 6 comma 2. I'm going to try and obtain this unit vector by scaling the given vector by a certain number. I want c times 6 comma 2 to be a unit vector in the end. To determine what value of C I should use, I'm going to again use this principle that I should scale by the length that I want divided by the length that I currently have. The length that I want is 1 unit because I'm trying to create a unit vector. The length that I currently have has to be calculated using Pythagorean theorem. So that looks like the square root of 40. So now, using my desired length and my current length to build the scalar C that will turn this guy into a unit vector, the length I want is 1, the length I have is square root 40, that's being applied to 6 comma 2, so that's giving me the vector 6 over root 40, 2 over root 40. This is now a unit vector, a vector of length 1 in the same direction as 6 comma 2. 6 comma 2 is sticking out here 6 units along positive x, 2 units along positive y, and it currently has a length of 40. And the little vector that we have just found is pointing in that same direction, but it's shorter. And now it has a length of only 1. So, to summarize, if you want to take a vector and change its length, then you can do that by applying a scalar multiple. Specifically, what scalar multiple should you apply to change a vector's length to some desired result? You apply a scalar multiple in the form of a fraction, where the length that you want is in the numerator, and the length that you currently have is in the denominator. This fraction, used as a scalar multiple, will change the vector's length from whatever it is right now to whatever length you desire. Now, up to this point, we've been operating mostly with positive scalars. So let's think a little bit about what would happen if we're dealing with a negative scalar. For example, if I take the vector negative 2 comma 1 and I scale it by a negative number like minus 1. My original vector v points 2 units in the negative x direction and 1 unit straight up. When I scale the vector by a factor of minus 1 and apply that scalar component-wise, that flips the signs of both the components, so that's now pointing 2 units in the positive x direction and 1 unit straight down. So what I can see is that this negative scalar has had the effect of flipping the vector in the opposite direction. So positive scalars change a vector's length without changing its direction at all, whereas negative scalars flip the vector in the exact opposite direction. Negative scalars flip the vector in the opposite direction. To give you an example of this principle in action, consider the following example. We've got an object who's moving along a direction given by the vector negative 1, comma positive 1, comma positive 3. While it's moving, it's being acted upon by a force of friction with a magnitude of 7 newtons. So let's go ahead and find this friction force. Now, the object is moving along this direction. Let me nickname it D, as I have done in the past, direction vector D. So if I just draw a little simplified sketch, because I don't want to do the full 3D picture, it's going to be too complicated. A little simplified sketch, maybe the vector D, roughly speaking, looks like this. The friction force is acting to resist the object's movement. So it's acting in the exact opposite direction as the object's moving. So the force of friction is coming in here and pointing in the exact opposite direction with a magnitude of 7 units. So let's try and use this information to find the friction force as a vector. So the first thing I'm going to do is I can apply a negative scalar to the direction vector, and that's going to flip it in the opposite direction. So if I think about negative d, which is equal to 1 comma minus 1 comma minus 3, that's going to be the vector v flipped in the opposite direction. But perhaps the length of negative d is not quite correct. The length of negative d is whatever it is right now, and the friction vector is supposed to have a length of 7. So let me rescale the vector negative d to take it from whatever length it has right now and turn it into something of length 7. If I rescale negative d so that it has a length of 7, then it will be equal to this friction force vector. The current length of negative d, using the Pythagorean theorem, is negative 1 squared plus 1 squared plus negative 3 squared. So that looks like square root 11. So now let's take the vector negative d and apply a scalar multiple. The scalar multiple that I will apply is a fraction. In the numerator, it's going to be the length that I'm trying to create. I'm trying to create a friction force vector with a length of 7 units. And the length that I currently have, that I'm trying to get rid of, is this current length of square root 11. So I will use this fraction, and I will apply it to my vector negative d, in order to change the length from square root 11 to 7. So that gives me the vector 7 over square root 11, negative 7 over square root 11, and negative 21 over square root 11. This vector can now serve as a representation of my friction force, because this vector now points in the correct direction, opposite the direction of movement, and it has the correct magnitude, 7 units. So this would be my final answer representing this friction force. This concludes our lesson on vector length and scaling. The length of a vector, typically denoted by a pair of vertical bars or a double pair of vertical bars, can be found using a Pythagorean theorem type of formula. The square root of x squared plus y squared plus, if you have a z, z squared. Unit vectors are vectors that have a length of exactly 1 unit. So to determine if a vector is a unit vector, just calculate the length and see if the result is equal to 1. Scaling a vector is the act of multiplying a vector by a scalar. And scaling a vector is performed component-wise. When you scale a vector, in particular when you scale a vector by a positive number, that has the effect of changing the vector's length without changing its direction at all. If you use this principle, you can take a given vector and change its length to whatever you want. If you have a vector and you want to change its length to some desired outcome, you scale the vector by a fraction. The fraction where the length that you want is in the numerator, and the length that you currently have is in the denominator. And then if you want to flip the vector in the opposite direction, if you want to change the direction of the vector to its exact opposite, you can do that by applying a negative scalar instead of a positive one.